right, in today's pre-lecture, we're going to talk about more on linear codes here. So this is in chapter 14 of the textbook. So talking about how we can tell the minimum distance of a linear code, and then also a method for generating linear codes, which are a special case called cyclic codes. So we're not going to cover everything in chapter 14, but I just want you to see these things so you've got some familiarity with them. So this is going to be short, so you can also take some time to review the stuff that we covered on Friday, because that will also be going into the group work on Monday and, of course, on the homework. So let G have this form where it's the identity matrix, K by K identity matrix, and then there's also another matrix A by it there. So we saw this on Friday. We were working with matrices of this form. Let this be a generating matrix for a linear code. And then we found that H equals minus A transpose I n minus k is a generating matrix for the dual code. And we can use this matrix to figure out if vectors are code words in the original code by checking if V times H transpose is equal to 0. So in addition to being a generating matrix for the dual code, we say that H is a check matrix for the original code here as well. So for an example for how we use this, for the code C with that generating matrix there, let's say this is over F3, and we want to check if V equals 1, 0, 1, 1, 1 is a code word. So the way we're going to do this is by building our check matrix and then using that to figure out if this is a code word. So here, looking at our generating matrix, this has that special form that we're looking for. So we've got the identity matrix there, and then A is just going to be the rest of this matrix. So we've got A is equal to 2, 0, 1, 1, 2, 0, and then A transpose is, so flipping rows and columns, we've got 2, 0, 1, 1, 2, 0. So then we'll have H equals, we've got minus that first of all, and then the 2 by 2 identity matrix. And we can rewrite this without those negatives in F3. So we can write this 1, 2, 0, 1, 2, 0, 1, 0, 0, 1, like that. So this is our check matrix. So then to see if that vector V is a code word, I've got 1, 0, 1, 1, 1 times, and then we're multiplying that by the transpose of H. So multiplying that by 1, 0, 2, 1, 0, 2, 1, 0, 0, 1. Okay, so all we have to do is then multiply these and see if we get the 0 vector. So multiplying first, going here and here, we've got 1 plus 2 plus 1. So we end up with 4 or 1 there, since we're over F3. So we can already see this isn't going to be the 0 vector, so we can tell that isn't in there, but we'll finish the computation anyways. So we've got 1 times 2, so 2 plus 1. So we do get 0 for the second component, but still that's not equal to the 0 vector. So V is not a code word. So this is how we can check if words or vectors are code words in the original code by using that check matrix, which is also the generating matrix for the dual code. So then now moving into the chapter 14 material, let C be a linear code with generating matrix G and check matrix H. Let D be the largest integer such that any, so really important here that this is any D of the columns of H are linearly independent. So it's not just like we can find 2 linearly independent columns or however many linearly independent columns. It has to be true for any columns. Then C has minimum distance D plus 1. So this gives us a nice way to look at the check matrix and just see from that what the minimum distance of the code is. So that's without doing any sort of computation of like, here are all the code words and trying to find the distances between all of them. This makes this a lot easier, where we can just read it off of this check matrix and avoid a lot of extra computation. So remember our check matrix that we found on the previous slide. We had H equals 1, 2, 0, 1, 2, 0, 1, 0, 0, 1. So we want to see what's the largest integer D such that any D of the columns of H are linearly independent. So certainly, since we've only got, looking at the columns of these are vectors with 2 components, so certainly any 3 won't work because that's impossible for 2-dimensional vectors. Now let's see, is it possible that we can pick 2 columns which are linearly dependent, which would reduce us down to 1. So in fact, if we look at these 2 columns here, 2, 0, and 1, 0, we can see that those are linearly dependent. So 2 doesn't work for D here, and in fact the largest integer such that any D of the columns of H are linearly independent, that's going to be 1. So D equals 1 here, since we can find 2 columns where they're linearly dependent. So D equals 1, so that means that the minimum distance of the code is 2, which is D plus 1. So this gives us a nice quick way to figure out the minimum distance of the code, and remember that was important from theorems that we had earlier in the course about how many errors we can detect and correct. So this is a nice way to figure out the minimum distance of a linear code. So now we're going to look at a way to generate linear codes rather than just kind of randomly picking some row vectors and hoping they work out nicely and are linearly independent. So the idea for cyclic codes is that if we start with some vector and then start rotating the entries, we can often get some linearly independent vectors. So we're looking at how we're picking out some rows for our matrix, and this is one way that we can sort of easily get some linearly independent vectors. So for example, if we look at 0, 1, 1, 0 in F7, 4, let's say, so then the way we get other vectors from this is by rotating the entries. So we'd have 0, 0, 1, 1 for the next one. So all we're doing is shifting everything one place to the right and then kind of wrapping around. So this 0 ends up in the first place. And then keep doing that to generate more vectors. So we've got 1, 0, 0, 1, and 1, 1, 0, 0. And if we do this again, we're going to end up back where we started. So something to notice here is that there's not really any guarantee that these end up being linearly independent. It usually happens that a lot of them are going to end up being linearly independent, but you still do have to pay some attention to if you're getting linearly independent vectors. So there are some results in the book about that make this work a little bit nicer so you have a better idea of what's happening. We're not going to cover those in the interest of getting to more codes, but I just want you to be aware of sort of very basics of how these cyclic codes work. So looking at these vectors now to see if they're linearly independent, notice that this guy, the last one that we wrote here, is equal to the sum of the first 3. But the first 3 vectors are going to be linearly independent, so if we use those 3 as row vectors, we can get a generating matrix for a linear code. So we can have 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, and that would give us a linear code here. So we can use this to generate linear codes. Another way that we can view this is identifying the vector with a polynomial. So take the entries in the vector and let them be coefficients of the polynomial. So taking b0 up through bn minus 1 and identifying that with b0 plus b1x plus b2x squared, and so on. Then when we're doing this right rotation, that's going to be the same as multiplying by x in this quotient field, or in quotient ring. So this is fq adjoin x mod the polynomial x to the n minus 1. So the way that this looks is, so we were starting with 0, 1, 1, 0, and that corresponds to x plus x squared, matching those coefficients up with the entries. And then once we rotate this once, we've got 0, 0, 1, 1, which corresponds to x squared plus x cubed, which is multiplying the previous one by x. And then rotating again, got 1, 0, 0, 1. That's corresponding to, and if we multiply the previous one by x, we get x cubed plus x fourth. But we're looking inside of the ring FQ, so it was F7 for our particular case. F7 adjoin x mod x, so n here is 4, so x to the fourth minus 1. So in here, x to the fourth is equal to 1. So this is equal to x cubed plus 1, and that makes sense with how we're corresponding those vectors with polynomials. Then finally for our last one, we had 1, 1, 0, 0. There we had okay, so just realized I was sort of accidentally doing F2 math on the previous one, so it's not quite the sum of the first three here, but it's the first minus the second plus the third. So let's correct that quickly. Okay, so this was first minus second plus third. Sorry about that. But anyways, so this one's corresponding to x to the fourth plus x, and x to the fourth once again is the same as 1, so we've got 1 plus x there. All right, so this is how we can generate some linear codes using starting with a single vector and rotating the entries, and we can also identify this with polynomials and think of it as multiplying by x in a familiar quotient, or modding out by a polynomial ring, which we've worked with before. So that can be a handy way to work with these codes and get some results out of that. All right, so that's it for this pre-lecture. So make sure you answer the questions and take a little bit of time to review the material from Friday on dual codes and syndrome decoding.